but integrals involving natural log. Slightly different. Meaning that what's going to happen is we're going to start getting ln x as the answer to our integrals. We don't know how to integrate ln x yet. We won't learn how to integrate ln x for a while. But we do know how to integrate 1 over x. Right? So the whole crux, everything that 5.2 centers on is this integral. And how we can exploit it again and again and again and again. So you remember what we decided this integral was going to be? Natural log of absolute value x is the best fit for our integral here. So basically in 5.2, 5.2 is broken into kind of 2 parts as far as the content goes. The first part is figuring out how many different ways you can exploit this formula. Right? Mr. Larson gets super creative and gives you a bunch of different integrals to try. The second part has to do with integrals of trig functions. So first, let's see if we can use this formula in some different examples. Start off with something. The indefinite integral of 1 over x minus 5 dx. What do you think this should be? ln of absolute value x minus 5 plus a constant. Why? Okay, let me not answer why yet. Let me give you this again instead. Suppose I make it 2x minus 5. What's the integral of 1 over 2x minus 5? Do you think it's this?
That would be too easy.
That'd be too easy, right? Why isn't it this?
Because that's not the derivative.
If you do the derivative of this, you would get 1 over 2x minus 5 times 2. Right? So if you do the derivative, you're getting an extra 2 that you don't have here. So there's 2 ways to take care of that. You can either be clever and say, fine, I'm going to put a 1/2 out front. Then when you do the derivative here, the 2 will cancel with the 1/2 and you'll get exactly this. So that's the quick way to do it. What's the other way to do this integral? Well, this is technically a u substitution. Right? If you don't really understand where this 1/2 came from, then you would have to do this integral using u substitution. Or, if you want to do the integral of 1 over 2x minus 5, because it doesn't fit this format exactly, you change it using u equal to 2x minus 5. Then du is equal to, well, du dx is equal to 2. So du is equal to 2 dx. Right, so to finish off the u substitution, you have to put a 2 up top, which is where the 1/2 is coming from. Then the integral becomes 1/2 integral of du. This is du over u. And that fits this formula perfectly. So 1/2, the integral of du over u is ln absolute value u. And then you put your u back in. 2x. Also constant. So, it's up to you which way you want to do it. I don't really care as long as you get the 1/2. And if you forget the 1/2, it's wrong. Minus 1,000. But if you have the 1/2, then you're right. And I don't care whether you do it by u substitution or by reverse chain rule. It's all the same to me. But be careful of that. Why didn't I need a constant in this case? Right, I didn't divide by anything out front here, right? Because the derivative is 1. Right? So as long as the derivative of the bottom is 1, you can just do ln of the bottom as your integral. But if the derivative of the bottom gets more complicated than 1, you have to technically do a u substitution, or at least fix it up with a chain, with a reverse chain. Okay. Now, grease here. Integral of x squared divided by 4 minus x cubed dx. What do you think? I don't think. Yeah, so hopefully what you're noticing or you're starting to pick up on is there's a relationship in a lot of these integrals where the top and the bottom is the derivative of the other one. Right? So x squared is basically the derivative of x cubed. It sets you up perfect for u substitution. So you set u equal to 4 minus x cubed du dx equals negative 3x squared. Right? The derivative of 4 minus x cubed is negative 3x squared. So then du is equal to negative 3x squared dx. I have this, I have this. I don't have that negative 3. I have the x squared, I have the dx. I don't have the negative 3, so I put it in. Negative 3 up top, negative 1/3 out front. Now we actually have to now we have to convert to u's, so we can do the integral. This will end up being negative 1/3 integral of the whole top is du, and the whole bottom is u. Once you have that 1 over u or du over u, you use your formula. The integral of 1 over u is ln of absolute value u. Also constant. Don't forget to put your x's back. Slightly trickier one here. d integral of x cubed minus 8x over x squared dx. How do you feel about u substitution for this bad boy?
Would it work if you solved for u? I mean, solved for x.
So, wait, what do you want to make u?
Like if you made x squared u, and it would be 2x. Would be du. And
So then up here, maybe if you factor this,
yeah, like you factored out the x. Then you multiply by 2.
so then in here you have u minus 8. Yeah, you'll have to multiply by 2. And then that'll be your d, this should be dx. Yeah, that'll work. That should work.
You just have a bunch of fixed numbers.
So you can force u substitution here. Do you need u substitution? What should you, what else could you do?
Factor out.
Yeah, you can separate this. Right, since there's a single denominator, you can separate this out into the integral of x cubed over x squared minus 8x over x squared. Yeah, so the integral of x minus 8 over x. And each of these is pretty simple, right? X becomes x squared over 2. What about minus 8 over x? What's the integral there? ln 8x. 8 ln x. 8 ln absolute value x. Right, the 8's a constant multiple, so it just tags along. Right, this is a constant multiple of 1 over x. So the u substitution will work here if you force it. Also division, if you just divide the x squared into both terms, that'll get it.
If you had a power on x,
Yeah.
move out. Can it move out of absolute value?
Yeah, if you end up with like ln of x squared, you can get rid of the absolute value altogether. If you end up with ln of x cubed, you can put the 3 out front and just have absolute value of x here. Yeah, so in general, I think to answer your question, absolute value of x to any power is equal to absolute value of x to that power.
Okay, and then you can just move that out front.
Right, and then you move that up front. Right, because whether you do the power first and then make it positive, or you make it positive and do the power, it's gonna get you to the same place. I'm going to go with ln x over x dx. So there's definitely not any algebra tricks I can do here. I don't know the integral, I mean, it doesn't fit any of my rules yet, so I'm going to try u substitution. What do you think I should make u equal to? I only have two choices. I can either make it x or ln x. I can make it 1. So let's make it ln, right? If you let u equal ln x, derivative du dx? 1 over x. So du is 1 over x dx. So my du is sitting right here. Think of this as an extra 1 on top. You have 1 over x dx. So all of this is my du. Leaving only u left on top. So this equals the integral of u, because that's all that's left, du.
When you do the derivative on that one, since the ln is not absolute value of x, does that change your domain?
Yeah, the domain on the derivative would have to be x greater than 0 for this one.
And you have like...
Everything in this problem is x greater than 0 because of...
Okay.
But it does, I mean, basically I could have put absolute value x here and done everything the same. But, like, it doesn't matter. But the integral of ln absolute value x over x and the integral of ln x over x are going to be the same, except for the domain. But let's finish this off. So the integral of u is u squared over 2 plus a constant. So then I plug my u back in. So I get ln of x squared over 2 plus a constant. So how would you know to do this substitution here if you just saw this on a test or a quiz?
You can't figure anything else.
Well, one, you can't think of anything else to do once you start doing funny things like canceling the x's. But two, you're always looking for that pattern in integrals now where you have a function and its derivative, right? You have ln x and the derivative of ln x. Right? When you see that pattern, a function and its derivative, you know you got to try use it.
Or at least almost its derivative.
Almost its derivative, right? Approximate is pretty close, off by a constant. Okay, okay. So. So this is essentially the same pattern, right? Because you have ln x, and you have the derivative of ln x. So you're going to set up u substitution with u equal to ln x again. Because then when you do the derivative, you get 1 over x. Which means that du is equal to 1 over x dx again.
This one's just going to be u to the negative.
Yeah. So when you substitute in here, all of this is your du. And then this guy left over is your u. Excuse me. So you get du over u. And we know that when there's a u on the bottom, you'll get ln of absolute value of u plus a constant. Plug back in your x's. Plus was it? ln x was u, right? ln of absolute, or ln of absolute value ln x. Let's see. Do you need the absolute values? Because by assumption, as soon as I write ln x, I know x is positive. So are these absolute values doing anything?
They're like making your domain
Um,
I guess it's not.
Even though x can only be positive, ln of x can still be negative. Right? If you think about the graph of ln x, it looks like this. So if I take off these absolute values, then I wouldn't be able to put in any x values between 0 and 1, where my function is negative. On this interval, ln of x is negative. So the absolute values are actually allowing me to plug in x values from 0 to 1. So they are making a more general, a larger domain. Okay. Let's see. Find the area of the region. So I'll give you the function y equals natural log of square root x over x. And I'll give you x equals 1 and x equals e and y equals 0. Alright. I just made this up, so hopefully it works out nice. Not, my apologies. So how do we approach this problem? Yeah, so whatever this function is, I don't know what it looks like. Alright. But it's some function, ln x over, ln root x over x, so whatever it is, some function. Who knows? And I want to find the area from 1 to e. So here's x equals 1. Here's x equals e. So I want this area under my function, because I'm also bounded by y equals 0, which is this line here. So the way we find area under a curve, or area of a region under a curve, is to integrate. So what integral am I going to set up here?
Just the definite integral from 1 to e.
Definite integral from 1 to e. So my area is going to equal the definite integral from 1 to e, from here to here, of this guy. dx. Okay, so now I have to actually calculate this integral. What do you think? U substitution, U equal to? Yeah, you probably could do that. I mean, that's, yeah, I mean, sure, whatever. But if we're going to make our lives a little easier, I'm all about making my life easier. Maybe we can get rid of this root. What do we do with roots inside LNs? Make them 1/2 power and pull it out. So we can change this to ln of x to the 1/2. And then this 1/2 is going to come down in front, which will then just get pulled out of the integral. Out front, ln x over x. This guy we can do, in fact we just did it. Right, this guy we did by setting u equal to ln x, because then du would be 1 over x dx. So we change this by setting u equal to ln x, since we have 1 over x in there already. We change this guy to u du. From limits from x equals 1 to x equals e. Right, remember these are x. So the integral of u becomes u squared over 2. From x equals 1 to x equals e, 1/2 out front. Change back to x's. U is equal to ln x. We evaluate from 1 to e. So 1/2 times ln of e over 2 minus ln of 1 over 2. All right, when you do definite integrals, top minus bottom always. So what do we end up with? 1/4 altogether, I think, right? ln of 1 is 0, so this guy's useless. ln of e is 1. So 1/2 times 1/2. 1/4. So if your problem has you find the area of a region, you just need to set up your definite integral. And whatever the definite integral is, maybe it'll involve a natural log, maybe it won't. Right, but this is a more general problem. Find the area of a region, do a definite integral, always. Remember, when doing derivatives and integrals of ln, it's going to be a little bit easier to apply your algebra first, I think. Your log rules first.
Did we drop the square?
Oh, did I drop the square? Yeah, I think I intrinsically was thinking about the answer. This should be squared, so this will be squared. 0 squared is still 0, and 1 squared is still 1. But yeah, those should be, for proper work, they should definitely be squared. Thank you. Okay, so the last thing in this section, we're done with natural log forever, is all of our trig integrals, our new trig integrals. So we saw, we had, just to remind you, we had sine and cosine. The integral of sine x was what? Negative cos x. Plus a constant. got to be negative because when you do the derivative of cosine, you get negative sign. And then we knew the integral of cos x, which is regular sine x. So then we have four other functions we need to come up with the integral for. Cotan, tangent, cotangent, and secant, cosecant. These guys we saw in the last section, we came up with a derivative that was equal to tangent, so we knew what the antiderivative was. It was negative natural log of cos x. And most generally, you can actually get away with an absolute value. And then secant was natural log of absolute value secant x plus tangent x. Cotangent and cosecant follow the same pattern. This guy will be natural log of absolute value sine x. And this guy will be natural, the negative goes away here. And this guy will be negative natural log, pick up a negative on this one. Those are the integrals of your 6 basic. Alright, run out the clock here with some examples of this, and then we'll 4 next time. So find each indefinite integral. Integral of 2 minus tan 3x dx. How can we do this integral? So you can do it separately. You can integrate 2 and integrate tan 3x. 2 is easy enough, 2x. Minus. The integral of tangent x is negative natural log absolute value cos x. What's this 3 going to do? Multiply by 3? Divide by 3 because you're doing an integral. Right? You have to do reverse chain rule for this 3. And you'll get negative natural log of absolute value cos 3x, but then you get a 1/3 out front to make up for the chain rule you would do when you derived. So always, 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 if you put an extra constant in here, a constant multiple times x, that's going to come out as a division when you do your integral. It's just the opposite of the chain rule. You're making up for the chain rule. The other way to do this would be u substitution, right? If you didn't believe me, you thought I was yanking your chain, you would set u equal to 3x and then the 1/3 would come. So what about the integral of tan x times natural log of sine x? Oh, this is supposed to be. Sorry. So what do you think?
U sub
Yeah, what does u have to equal?
cosine. Tangent.
Should you make u equal? Okay. Now you're thinking about it backward. If you make u equal to tangent, you would have to do the derivative of tangent. What's the derivative of tangent? Secant squared, right?
The derivative.
The derivative of tangent secant squared, that doesn't match at all. Right? That doesn't match ln cosine. So you could try maybe u equals cos x. Does that give you? Then the derivative would be negative sine x. So that would be u, but that doesn't take care of this tangent.
Could be the natural log of cosine.
Yeah. So you need to set u equal to the natural log of cos x.
It's going to almost be negative.
Natural log of 0. Because now when you do the derivative, you get 1 over cos x times negative sine x. Right? Derivative multiplied by the derivative of the inside. So sine over cosine is tangent. This becomes negative tan x. So du is equal to negative tan x dx. This works. I have to fix it up a little bit because I don't have that negative. So I put one on the inside, one on the outside. So what am I going to get here? Negative integral of. This is all du. Negative tan x dx is du. And then ln of cos x is du. Negative u squared over 2. Also constant. Negative ln of cos x squared over 2. There's no, with derivatives there's a process, right? If I throw you a function and I say take the derivative, you say, all right, I do chain rule, I do quotient rule, I do product rule, there's a process. With integrals, there's not really a process. You just say, how can I manipulate this to apply one of my formulas? A bunch of different possibilities. Makes integration a lot difficult. Integral of secant x cotangent x. Now remember, there's no product rule, at least we don't know a product rule for integrals. All we know is a bunch of formulas and u substitution. That's it. Is u substitution going to work here, you think? What's the derivative of secant? Secant tangent. Well, that ain't cotangent. What's the derivative of cotangent? Cosecant squared, negative cosecant squared. That ain't secant. So u substitution isn't really getting me anywhere, at least not at first. What else might I try?
Manipulate things.
It would be 1 over cosine.
Some sort of identity, right? Some sort of manipulation to simplify this. I don't have any tricky identities. All I really have is that secant is 1 over cos, and cotangent is cos over sine. So the cosines cancel. You're left with 1 over sine. How do you integrate 1 over sine? Is it ln of sine? That's funny, huh?
Oh,
So first you change it to something you know the integral of. Right? Change 1 over sine back. What's 1 over sine equal to? Yeah, so 1 over sine is equal to cosecant. Right? Trig identity, cancel, then another trig identity, back. Because I know the integral of cosecant. So I canceled and manipulated and did everything I could to get to a function that I know the integral of. The integral of cosecant is the negative natural log of the absolute value cosecant x plus cotangent x. What changes, just out of curiosity, if I gave you this, I square them both.
Just take it.
It's going to be negative ln squared.
no.
That was, no.
The cosecant squared, so it would be cotangent.
Yeah, so now you're going to do all the same simplifications. 1 over cosine, but it'll be squared. Cosine squared, sine squared. So you still can't do any clever substitutions because you don't have the right derivatives. But you can simplify this with simple identities. But in this case, I end up with 1 over sine squared, which is cosecant squared. Now be careful, if you're doing the integral of cosecant squared, you don't need this huge mess. We knew the integral of cosecant squared before we even knew what natural log was. Right? The integral of cosecant squared is negative cotangent. Because the derivative of cotangent is negative cosecant squared. One more quick comment. So, u substitution also is valid when you're dealing with any integral. The other thing you want to keep in mind is any sort of identities that will make your integral simpler. One last thing I want to mention, if you don't remember, because you just have a crappy memory and you can't be bothered to remember integrals, if you don't remember the integral of tangent x, how can you do it without a formula? The integral.
Oh.
What's tangent of x equal to?
Sine of x over cos.
Sine x over cos x. Now, how can you do this integral?
Break it up into
Use substitution! Use substitution! Ah! Love use substitution! Because the derivative of cosine is sine. Well, almost. Close enough. So you can break this up into u equals cos x. So then du dx is negative sine x. So du is negative sine x dx. I have sine x dx, so I toss a negative in there to make the world a happier place. And this just becomes the integral of du is on top, u is on bottom. So you get, what's the integral of du over u? ln of u. No, no square. No, no. Stop saying square. Stop being wrong. 1 over u, the integral of 1 over u is ln u. Forgot my minus. Plus constant. So altogether I get exactly what I expected. Negative ln cos x. So it might take you a little longer, but you can do the integral of tangent without remembering anything really, except, well, okay, a little bit. You have to remember tangent is sine over cosine, which I hope you remember anyway. And you have to remember that 1 over u integral is ln u.